OK. So with the English language walkthrough out of the way, now we can start thinking a little bit about how it's implemented. So fair warning, you're going to see some implementation details that are a little bit gory and detailed. So we're going to try and show you as much of DNSSEC as we can. We'll show you all the little edge cases and implementation details. You don't have to know most of them. This is not a test of how well you know the exact way that DNSSEC works. And we'll try to highlight slides in blue whenever they're not as important for you to know. But I think it's an interesting exercise in designing something that's backwards compatible. So that's why we're showing it to you. But do be warned, it gets a little bit messy. OK, so here's one example of something that's a little bit messy. It's the fact that the DNS packet format has already been defined. Remember that everybody using DNS agrees that the DNS header looks like this. The first 16 bits are the ID. The next 16 bits are the flag, or however many bits the flags are. I don't think it's exactly 16. But this is a fixed header. Everybody agrees that the first 16 bits are the ID number. You can't come along and say, well, now the ID number is 32 bits. People won't know what you're talking about. So this header structure is already fixed. You can't change it because everybody is assuming that the header looks like this. OK, I guess I lied. There are 8 bits for flags. And that's a fixed number. So everybody in the world knows that when you get a DNS packet with ones and zeros, you start at bit number 16, and you go to bit number 24. And those are your flags. They're in the same spot every single time, and those never change. So what if you wanted more flags? So there's a bunch of stuff you might want for DNSSEC. For example, maybe you want a flag to indicate whether or not DNSSEC is turned on. You might want to set a bit to 1 if DNSSEC is enabled, and turn it to 0 if DNSSEC is not enabled. Maybe you want a flag that says, I do support DNSSEC, but I don't really want DNSSEC right now. I just want regular DNS for some reason. Maybe you want a flag for that. So the punchline here is that there's only 8 bits for flags, and they're fixed. But with DNSSEC, as we're extending the protocol, you might want more flags. So how do you get more flags for DNSSEC? You can't go and change the way that this packet looks. This is fixed. Everyone agrees that bits 16 through 24 are the flags. You can't say that bit 25 is also a flag. Not everyone's going to agree on that. So where do you put extra flags if they don't fit in the header? This is a backwards compatibility issue. If there's an existing protocol and you want to improve it, you might not be able to go back and redesign things like this from scratch. So you have to get clever. And this is one case where we get clever. So the way we're going to be clever is to add an extra record. Remember, there's no limit on how many records you can put in a DNS packet. Well, I guess it's subject to UDP limits, but in general, you can put a decent number of records in there. So why don't we just put an extra record in there and put the flags in a record? Now, is that the cleanest possible design? Probably not. It would have been nicer just to have more flag bits up top. But since you can't do that and you want backwards compatibility, we can just add an extra dummy record. And in that record, instead of storing actual data, like IP addresses or domain names, you'll just store the flags in the extra record. So that gives rise to this fancy name. It's a record with a new type that you haven't seen before. And that's where you put all of the extra flags and settings that DNSSEC needs. They don't fit in the header because there was no space, and you can't change the header. So we cheated by adding an extra record and putting all of our settings in there. So you don't have to know exactly how any of this stuff works. But the takeaway, I think, from a design standpoint, is that because we have to maintain backwards compatibility, you couldn't go back and change how DNS worked. You had to add extra functionality in a somewhat clever way, like adding a new record to store your extra metadata. So that's one example of something people had to do when they were implementing DNSSEC. OK, this one is useful to know. So remember that DNS records have name, value, and a data type. And if you remember our sample DNS lookups, you might remember that sometimes you get a lot of records back. So for example, when we sent out a request for eeks.berkeley.edu, the root name server redirected us to 13 different .edu servers. Any of them would have worked. They were there for redundancy, but we got 13 different records. It would be kind of annoying to sign 13 different records and provide 13 different signatures. That's extra work for the name server. That's extra work for us to verify. So one little trick you can do to avoid having to generate 13 different signatures, which would slow things down, is to sign a bunch of records at once. So one thing you can do is combine a bunch of DNS records. If they have the same name and the same data type, you can form a resource record set and then just sign them all at once. So this is another optimization we did in our design. Instead of signing every single thing separately, whenever there's similar data, for example, if one domain has a bunch of IP addresses, you can just sign them all at once, and that saves you a little bit of time and energy.